Cool. Um, oh God, I look like I just came back from a marathon or something. I don't know. Anyway, messy life, messy hair. What are we doing today? So we're kind of a bit going farther with the rethinking of the model, right? And if you've been following some of the voice notes that I put in Twitter, and if not, I recommend you to do that so you can actually go and check them with this hashtag voice notes. There you go. So these are just all the notes that kind of record voice notes when I'm just out there on the in the real world, and I kind of have a bit of a niche to think about some of the stuff. And then I've also got some text notes, which are just basically specific tweets of just my thinking, right? But nevertheless, so what I've been doing a bit of playing with this stuff here. So with a model, right? And I kind of came up with the. Let me see if I can show the Twitter one here. I think this is this one, yeah. So basically, what I was trying to say here is that, um, like, how would you basically build these? How would you model the state after the control node in this case, right? Um, is this working well? Yeah, there you go. Right. So, well, you kind of have, it's if you if this is zero, then you kind of see that the probability of the qubits being zero, of each qubit being zero, is a bit higher than the probability of them being one. It's not 50-50, right? You can see this here, but still they're entangled. Uh, Whereas if it's one, you know for sure it's 1-1, so so then there's no entanglement. And I was kind of thinking that one way to see these, or one way to model these, would be by using something like that, right? Where you would say, so each color is a qubit, and then you have a so a hyperedge, first of all, at a top level hyperedge that tells you that whenever the target is one, then we know that this is that this hyperedge is that's the state the system is in, right? The other two are one, right? And the way you would read these pictures is say, well, like it's kind of like you ask questions, right? If I know this bit of information, then what do I know about the other qubits, right? So if I know that this is a zero, um, like I know it's not a one, so I know that they are both up here. They are not like this hyperedge is not where the system is. So we are not. This means it's a bit that this I have to formalize maybe this is the way this is interpreted, but this would mean that you know for sure that they are both not 1-1, right? It can still be that one of them is one, but they're not both 1-1, right? But the same, if you just know that qubit green is one, like that doesn't tell you anything. You still have a bit of a mixture here, right? And we can test that. We can check that quickly, real quick and quick. So this is these. If I know that this is one, and I wanna, and I do that here. Oh, no, zero. Sorry. If I know this is one, then like, then I don't like. You see, like I don't know anything about each qubit separately. That's what you still have a mixture. You're not you can't like the hyperedges don't tell you anything here, right? Yeah. And so yo so I think that seems to be a good way to think about this. Now, the whole thing is how do we operationalize these, right? Oh, thanks, Q study. And now I see that actually the things popped up in the screen. I have to edit I have to check. I didn't know you can actually overlay the comments because I'm using the better thing. Oh, there's a draw mode. Oh, I can draw stuff in here. Ah, interesting. Cool. Okay, that's nice. Yeah, but I have to draw on the actual stream, which is not always optimal, but I guess it's good. Cool. Um, so what did I want to do? Hmm. So I was kind of, basically thinking about how do you operationalize that in terms of the rules, right? And we said, you kind of have these nested rules, like the CC not rule would be something like, you know, match a one, and then so match a one for qubit zero, then match a one for a qubit one, and if so, then kind of do the 0, 1, 1, 0 kind of rule matching for this is already qubit 2, right? So you kind of have this double nestedness, which is what creates the hyperedges, because you initially have these, right? And this is in the 0 state. And so this is an LCOM, so you kind of, it's an LCOM match, so you would separate, you would separate the two and still have these, right? Then you go here and you go here and kind of separate that too, but because it's nested, you gotta nest it with the outcome match, right? So I mean now there's a normal match. So if we're here, right? So now there's an outcome match, and so you kind of would do the same here, but now you would wrap these two like these, right? Essentially, that's kind of what the nestedness is telling you, right? And then um, and then you have this, and then you have the 0, which kind of like you get the rule that says go from 0 to 1. So you take the 0 and you put it into 1. Because it's an LCOM kind of match, you're not getting rid of the 0. And because it's nested, then you wrap these around another time. And that's how you end up with that picture, right? So this is sort of what I have to program, I guess. That I think that's really what I want to do now. It's not only that, right? So I'm missing a part of this, which is what do I do when so the and what I've been thinking about now is like there's something missing in here, right? Which is what happens when, like, obviously these operation, right, won't do anything, like it won't turn your qubit into the same qubit, right away. The only thing this can happen is because you already have an initial state like this one. And now if I apply a CCX gate again, well, now I have a full match, right? So now I have like a full match everywhere. It's like one that matches with a one. And I have a full match for this rule here, which turns this one into a 0. And in this case, it will actually replace it because it's a full match, right? That's going to be tricky to implement. So it's going to replace it because it's a full match. So I'm going to do like this. But now, like, now this hyperedge this group here makes no sense anymore, because as I said, right, there's no information that you're explicitly storing there. Like regardless of the states, you know that this is always in the state zero. So like the fact that it's the same, it means that, so here algorithmically I can go and check, okay, so check that, and then so I should check all those that are zero. And in this case, because it's all zeros, right, then I would just get rid of these. So this would lead me into, merge the zeros. But what do I do with these things that is wrapped now into a hyperedge? Um, that's interesting, right? Because how you even interpret that? So if I do that, that literally just undoes it, right? Well, in theory, that kind of resolves everything that is in the hyperedge. This means that that hyperedge itself doesn't make any sense in and of itself. It's just, it was here as an element of that hyperedge, which doesn't exist anymore. And so I think just something that goes away as well, right? It's something that goes away as well, and now I guess the rule here would be, if you've got these things in the same hyperedge, you kind of have to recombine them again, right? And so you're back in there just because these happened. But it opens up a lot of tricky questions, right? We know what happens if this match is like across hyperedges. Hmm. Hmm. But this we can play with Quirk and figure it out, right? Like what happens if I'm here, but now I do a like these, right? Woohoo, nice. This is gonna be fun because then you have blah, blah, like an outcome, like a full match. Hmm. That's interesting, right? Because now you still have an uncertainty here. So it's not your uh, you will still that's for next time. I'm trying to figure out about the face kickback. So that's the face kickback part. Still knowing how to operate, how to evolve this is going to be complicated. The next, so the thing with the face kickback will be the following, right? So what if I have this initial state, right? And now you can see that this is not entangled at all. It stays as minus, but then there is these whole things here. They are both entangled, right? So, so, uh, so. But if I take a look at these, I see the entanglement is because this is what happened, right? So the phase kickback here. So this is the one element that had like no relative phase, and now has a relative phase. So this is what's happened, is that the phase has been kicked back, and so that's kind of like So the whole resolution is going to be one complicated beast in this whole thing. Um, yeah, because let's say that's where we start from now. So we start from these from the 0 plus 1, right? And I try to elaborate on that in the voice notes, but I'm doing it here again because there is complicated. So now you have kind of the same process, and I'll come here, and I'll come here, and then you're building this guy up here, and then you're like, oh, so now -1, and now comes in the operation and says, well, I'm gonna do the NOT gate, and so I end up with like a -0 plus 1, but I'm not gonna make a copy of these because it's the same, right? So there's no thing, no entanglement, no whatever. And so what I can just do is like I'm gonna get rid of these, but I have a global phase, right? This global phase is gonna be like, this is not equal mathematically. It's equal physically, but not mathematically. So I take this global phase of -1, and I'll just bump it up one level of the rule. Let's use just the rule, right? So the rule is this level nessedness, so we'll just bump it up one level. So we'll put it here. And now, yeah, and I think that should work. Yeah, okay, but now comes the problem, which is how come this resolves and that doesn't? Hmm. You know what I mean? Like I here I was just so happy to saying, well, because I resolve these, but in this case, it's like it never happened, but those are equivalent. So I cannot, and I cannot just now say, well, uh, because they stay entangled, right? They stay as mixed states. The phase got kicked back, but it and it's not, the thing is, the fucked up thing is that it's not that when one is one, we know the other one is one either, right? Like if I'm not here and I say like that's not true, I cannot just say if this is one and I plot blocks here, then this is minus. Yeah, of course. Then we know these. Hmm. And if it's 0, it's plus. Okay. Okay, that's weird. Why? Hmm. No, why? If this guy's 0, they should be minus. No. Oh God, I didn't think about this. That is actually complicated. I know that if I know this is 0, I know this is a plus. And the reason I know this is because this. So this guy is 0, right? It's either this or this, right? It's no, this or this or this. Because the minus is only in the 1 case. Ooh, so how do I know, how would I know this? What happens here? So what really happens here is I have that global phase here, and so I just kicked it out here, but I could have kicked it out somewhere else either, right? So, um, hmm. How to deal with these? Because oof, I mean, that is how? So how would I model that? This is a super weird edge case, right? I know that if this 0, then this is plus. Like how on earth would I do that? The only way that I would do that, would be able to do that, is if this minus would really somewhat belong to the edge, right? God. Because what that would mean is that the minus here only appears. Oh God, I don't know. I have to admit that that caught me by surprise. Like, but even my alt implementation wouldn't work there, I think. Would it? That's the thing, is like this minus is in a way only valid for the case where these two are 1, 1. That's why. And the same, that's why if I know that this is 1, right, that is going to be a minus. Cool. I guessed it. But if I know this is a 0, then this must be a plus. That is funky. Yeah. So the trick here is The okay, so the fact that they are both mixed makes sense, right? But like this means that I don't, these are not sort of consolidated back to these. Uh, God. And it might be just because of the fucking relative phase, you know? Oh God. It is a way to express that we know there, if we, but it's a different type of correlation. Is it? Fuck. Is it a different type of correlation? It's still entanglement, but it's not anymore a pure state correlation, but it's a phase correlation. Is that a thing? Phase mediated correlations. That is a thing. I can't believe. So I've learned something new. Or not. Let's see. In phase mediated correlations, in quantum field theory, whatever. Ah, so first tradition, the wave function occurring in the 50th correlation. Experimental studies of a system in a singlet state involve determining correlations that can exist between the two spins, even if they are separated. The states might contain small mismatches in the phases between the two spins. No, that's not what I mean. No. Phase correlations. Because that is a phase correlation, right? In a way, that is a phase correlation. So what's happening here is there's no correlation between the states per se. I mean, all possible values are there. Same probability of measuring everything. But the phase plays a role in answering the question. If I would have a way, do I have a way to say, for example, you know, no. Like, what if it is -1? No. Yeah, well, that's it, is it? So if this is -1, then this is 1. Whereas, if this is -1, then this is 1. Okay. Huh. So that actually shows me there's more to these that I have to figure out how to model, because I'm not saying you see that's the difference between this picture, right, and this picture here, right before that. So here, like, I have these, right? But now, like, whether this is 0 or 1 doesn't change anything. because there's no phase correlation. Crap. God. Why is this happening? This doesn't happen in 2 qubits, right? This definitely doesn't happen in 2 qubits. So what would happen if I would start with a minus state here, right? So say that I start with a minus state here. So what do we have now is that we have that after this CCX gate, if we know that if it's a 0, then this is a plus. Why? Because these minuses cancel, motherfuckers. Right? Yeah. So indeed, okay. So yeah. So that is what it. So I can't kick it up to any specific node. I have to kick it out in the correlation. That is the trick. Like, because there's a difference between saying, look, I'm starting at 0 minus 1 and 0 plus 1, God, 0 minus 1. And then, by virtue of the mixture, like this is going to kind of stay like this, right? But then there's a minus 1 associated to these. If I know that this is a 1, then that's going to be a minus. Boom. Because I know I've observed that value, but then I still have this guy that needs to go down here. Yeah. And if I know that this is a 1, that's going to be a plus, right? Because this and this will cancel. Yep. That makes sense. That makes sense. So they must stay there. So, okay, so I could kind of have the rule that says if the hyperedge has a relative phase, it means there's a relative phase correlation. It means I can't get rid of it. Why can I hear though? Because it was part of that. It was part of that thing up here, right? It was a nested hyperedge. But if this hyperedge would have had a relative phase, then I wouldn't have been able to do that. It feels so hacky. It definitely feels too hacky. But it is what it is. So this means I gotta keep track of This means I have to keep track of whether the edges are nested, right? Whether it's got a parent edge or not. That's nasty. So I need to be able to access this stuff. Hmm. I'm still thinking about, things beyond control, beyond beyond CK control nuggets and stuff like that. Um, but I guess it's a matter of finding the compositions and then doing this kind of stuff, right? It's just controlled operations. I think that's the key to implement that. It's the key to implement, and the other stuff you just. Yeah. Hmm. It's just because that relative phase gets kicked up here at the correlation level. Nasty. That is nasty. So if it's 0, it also has to be plus? How does it work now? No, it's minus. Look at this. If it's 0, it's minus. Why is that? Why is that? Yeah, okay. Yeah, of course. It's that because it's that because you ignore the phase correlation. This phase correlation only appears when the states are 1, 1, right? So in this case, you just ignore that and you just take that. That's why it's important to make a difference. In the previous implementation, I was not so sure what was the difference between having relative phases at the hyperedge level and having relative phases at the node level. And now this is clear. At least now this is clear, 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 clear. Um, the relative phases at the hyperedge level, it's another kind of correlation. It's a phase correlation. It's sort of a phase state correlation, relative phase state correlation. That's why if there's no relative phase, it's the same as not having one, because you're like, yeah. It's this it's still sort of the concept of like, cool. So now I've done these, so these are the same, right? Um, so these are the same. So I don't know exactly what is it that you destroy here. It's like, okay, so you don't draw that, or it's the same. So there's no need for that anymore. I don't know if you have to take them out or you have to take the zeros out or take the zeros in or just delete the hyperedge. I don't know what's the best approach. And then you would do that recursively. Then you would say, what about the other hyperedge? Or maybe maybe the trick here is that because there's no hyperedge in here, right? Because you can't just relate these guys, right? Then that's why this makes no sense, because it doesn't have the counterpart. Yeah, but that's fine. But like you really want the Bell state to be built like these, right? You must have the Bell state built like that. So if you have a 0 plus 1 and a 0 case, and that get, the rule is if 1, then do the whole 0 to 1, 1 to 0 thing. That's the NOT gate. So is an LCOM, so you mix that, and then you say, okay, so the 0 stays here, and now I match this one, I take this to 1, and I create that hyperedge. That's the delicate thing here is I'm kind of making some assumptions. Some things don't seem to work well with. If I get it to work for 2 qubits, I don't get it to work for 3, and vice versa. Because it's the combinatorial part that messes up with all these. Like here, that makes a lot of sense, but here it doesn't make sense at all. Because I want these to be like that. I want there to be a hyperedge here, because that's really what this is telling us, is that if no, yeah, well, yes and no, right? To be fair, yes and no, because it's something that it actually can be answered like that, because you're like, okay, so if you have this state, let's say you have this state, right? And I'm telling you that I know this guy is 0, then you know that it can't be 1, because then this would have to be 1, right? So it's 0. So you can answer the question. Whereas in this particular case, I think it's fine to have it like that, because if I tell you this is 0, you know this can be 0. So what you know is that these two can be together 1, 1. Okay, no, so it's cool. It's cool. I don't have to have it like that, and that was the main mistake. That's fine. That's correct for Bell state. That's actually correct for Bell state, because it allows me to answer these questions regardless. There's a symmetry here, right? So I could just as well have the hyperedge surrounding the zeros. That I wouldn't care about these. Like that could also just be yeah, whatever. Okay, cool. So that's fine. What have I discovered today? That I need that, and now, okay, but let's put us in this situation, right? So I think maybe the whole thing with the do I get rid of the high pressure or not logic has to be more complex. I think it's just too naive to just compare and that's it. It works for the 2 case, but it doesn't work generally here. Here, I don't want to get rid of the edge, because knowing the state of another of these, it tells me something different. It tells me information about the state of the other qubit. While here, right, let's say, Yeah, and here, the trick here is that knowing the state of these, right? Knowing the state of these doesn't tell me anything about the state of these two, right? Exactly. So this just goes away. In this case, knowing this state, it doesn't tell me anything about the state of these two, but I can't get rid of this because there's these additional pieces of information there in that relation that I can't, that is telling me that if these are two, yeah. So hyper edges don't tell you necessarily the full story, right? Like it's just because that piece of information that stays there. I think one thing that I have to kind of get out of my brain is the fact that if I see two states circled, three states circled, that I know that they must belong together. That's not what this model tells you. That's sort of that's a misunderstanding of these. Like in this case, if I know these, of course it doesn't tell me anything, but it's still this information is there. If this wouldn't be there, then this would just cancel. So the thing is that, and here, so okay, so here's the trick, right? So this means that whether a hyper edge stays or not, it's not something that can be decided by the hyper edge alone. It's something. So you probably have to ask two questions. First question is like, does this hyper edge have additional information? Does it have like a relative phase? If so, then I can't get rid of it. That's my current assumption. If not, if not, if not what? If not, do I? Is it really that they must kind of span across all the qubits in the system? That's also not true, right? Because maybe I just. So next question is this one, right? So what if I do these? Um, what if I do these? So this is where the model breaks, man. So what if I do these? So this is in the zero. Oh no, whatever. That's in the zero state. That's zero, and now I do like this, right? So that is actually this damn motherfucker here, right? That's where it breaks. Because these doesn't tell me anything about these two, right? It's not enough. Shit, it's not enough. There's something else there. I'm missing a piece of information to fully model these because I cannot, with this model, I can't distinguish between these and these. No, what? Sorry. What? No, what am I doing? What was that? Case. What am I doing? No, they go away. Yeah, okay, no, it's an intermediate state. It's not that I can't distinguish. That's not right. But it's just an intermediate state that is confusing me because I get rid of the zero, I get rid of the hyperedge, and then I'm left with these. So how do I know that I can turn this into that and that this is not this state? And that, sorry, that this is not the, um, this state, right? It's this kind, the resolution has got to be defined a bit better. Anyway, so it's almost there. I'm almost there. I feel like I'm kind of like almost there. It's just I have to kind of I just have to do that again, that exercise again. The hyper-H does not necessarily have the full answer. It's not telling you that's the type of states that like that. If you've got this one there, the other one is there. There's nuance to these. There's nuance to these, especially with multiple qubits. Like knowing that this is 0, 1 doesn't tell you about whether this is 0 or 1, but it tells you that it's both. Okay, that it's both 1, 1. So that definitely tells you. Oh God. Uh, Almost there. See you next time. I don't know if I can make it tomorrow. I'll do my best. Bye bye.